So again, today we're solving systems of equations, and there's three different methods that we're going to use to solve systems. But before we actually get into the different methods, what is a system? So anytime we talk about a system of equations, again, equations being plural, we're talking about more than one equation. So a system of equations is when you have more than one equation that are related to each other with the same variables. So a system of equations is when more than one equation is related to each other with the same variables. Now, most of the time, if we're talking about a system of equations, we're going to be talking about the solution being wherever they would intersect on a graph. So we're going to talk about three different types of ways to solve. One is solving a system by graphing. Then we also have solving by substitution. And finally, solving by elimination or combination method. So the first one, the graphing, is the most basic, because whenever we talk about a system, normally we're going to end up with at least two values being part of our answer. And normally, for everything we're doing in here, it's usually going to be an x and y value, so we can normally write it as a ordered pair or as a point. So the first one, again, whoops, I almost forgot to say, solving by graphing. So that's what we're doing first, solving by graphing. Now, when you're given a system, it's normally going to be written so that you have a brace with two different equations. So y equals 2x minus 2, and y equals negative x plus 4. Bless you. All right. So here we have two equations. Most of what we're going to be doing in here, if we're doing graphing, again, most of the other stuff as well, but graphing will almost always be linear equations. Now, if I was to give you anything besides a linear equation, I would probably just give you a picture of the graph. But essentially, if we're graphing two linear equations, we could graph each one of the equations separately and find out where they intersect. So on here, we have two equations. So the first thing we'd have to have is an x and a y axis. And then we're going to mark off, I'm just going to go 5 units in each direction. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4. So we have our coordinate plane. This is our x, this is our y. And if we graph these two lines, the first one, and we have a linear equation, 2x minus 2. The negative 2 is telling us where it's crossing the x-axis. So at negative 2, put a point there. That's our starting point. Then we have a slope of positive 2, so that means we're going up 2 and over 1. Up 2 over 1. Up 2 over 1. And again, that will give us a straight line. Then for the other one, same thing, except this one has a starting point at positive 4. So 1, 2, 3, 4. And we have a slope of negative 1. So that means we're going down 1 and over 1. Down 1 over 1. Down 1 over 1. Down 1 over 1. And again, that 2 will give us a straight line. So now, Where's our solution for this? Where they intersect. So right here, this point is at 2, 2. That would be our solution for this first question. That's just wherever they intersect. Now, most of the time on these problems, I will give you the equation. Sorry, give you the graph. If I don't give you the graph, then the equation will just be for linear functions. So there's really only 2 steps to this. Your first step would be to graph each equation, and the second one would be to find the points of intersection. So again, graph each equation, find the point or points of intersection. Now, will lines always intersect? Will 2 lines always intersect? No. So there's actually 3 different types of outcomes that are possible when we have 2 linear equations. So 3 types of outcomes for 2 linear equations. Like I said, the majority of what we're going to do is going to be linear equations. So I'm going to draw 3 graphs. Again, these would just be sketches, nothing fancy. First possibility is that we get 2 graphs, kind of like what we had on the first one. And those 2 graphs intersect. So we have a point of intersection, and where those 2 graphs intersect would be our solution. So in this case, we would have one solution. We could also have 2 graphs that are parallel to one another. If they're parallel, how many solutions would we have? No solution. Yeah, so this will be no solution because the lines are never going to intersect. The other possibility, and I'm doing this on purpose, I'm going to draw the same line. So I'm drawing it in 2 different colors here so you can see it. So the same line, right on top of each other. So there's 2 lines there. How many solutions would we have then?
2.
And more than 2. Infinite, yeah. So on this one, you can either spell it out or use the symbol for infinite, but there are infinite solutions. Now that's different than saying all solutions or all real solutions. And again, the main difference there is our only solutions occur along that line. So we can't say all numbers are all real, because if I picked a random point out here, that's not on my line. So it's not all solutions. There's an infinite number of solutions just along that line. Because again, that line goes on forever in both directions. So now, how do we come up with each of these? Well, the one solution is if the lines intersect. If lines intersect. The no solutions is if our 2 lines are parallel. If lines are parallel. Infinite solutions if lines are the same. If lines are the same. Now, you don't have to copy this next thing down. I'm just going to show you one other example of a graph real quick. But again, you don't have to copy this one down. So if I give you a graph, I don't necessarily have to make it two linear functions. Because if I had, say, a parabola, which we did in our last section, with a line intersecting, could you still identify your solutions? Could you still identify your solutions here from a graph? Yeah, because it's just wherever they intersect. Now, is that going to follow these rules? No, these are only for two linear equations. But again, I'd still be able to find solutions on a graph like this because I just have to look at the graph and identify, hey, it's intersecting here and here. So those 2 points would be my solutions. Again, I could potentially give you any type of graph I wanted to, and as long as the graph showed the intersections, you'd be able to identify those as solutions. So again, anywhere it intersects on a graph will be a solution to a system. So now, the next method of solving is going to be solving by substitution. Solving by substitution. Now, this one isn't the shortest process, all right? So I'm going to give you 2 equations. So here we have our system, y equals 2x plus 2, and negative x minus y equals 10. Now, we've used substitution all year long. Most of the times when we do substitution, we're doing one of a couple things. We're either plugging a value in and simplifying, or plugging a value in and then solving. Well, here, solving by substitution, we have 2 equations, 2 different variables. In order to solve by substitution, we're going to take one of those equations. We have to make sure it's set equal to a variable. So in this case, I already have one of them set equal to a variable. And we're going to take the equation that's already set equal to a variable and plug the entire thing into the second equation for that same variable. So that first equation is set equal to y. So the y then, in this equation, will get replaced by this entire thing. That whole thing is going to replace y in that second equation. So when we rewrite this, we have negative x minus 2x plus 2. So that whole thing went in place of y. And it's still equal to 10. So now that we replace that one variable with that other equation, we only have one variable left over. And we can solve an equation with one variable. We've done that all year long. So on here, we can go ahead and solve this. First, you'd have to simplify. So on this one, we could get rid of the parentheses after we distribute that negative sign. So that negative sign that's out in front, go ahead and distribute that to both of those. We now have negative x minus 2x minus 2 equals 10. We could combine like terms. We have a negative x, a negative 2x. That gives us negative 3x. We don't have any more like terms, but now we could go ahead and isolate the variable. So we want to get this variable x all by itself. So we could bring that negative 2 over to the other side. So add 2 to get rid of it. So negative 3x equals 12. Then we have negative 3. You could also get rid of that by dividing it over to the other side. So divide off the negative 3. And x would be negative 4. Now, is that my entire answer? No. That's my x value. But as we saw in the first set, my answers to this are going to be like points. They're going to be an order pair. They're going to have both the x and the y value. So we solved for half of it so far. Now that we know half the answer, though, we can take that value and plug it back in to either of those original equations. So we have 2 equations saying up there at the top. The first one is already set equal to y. So if I plug into the first one, I'll just have to simplify that one side of my equation. If I took this and plugged into the second equation, then I'd have to solve for y. So again, you want to plug it into whichever one you think is going to be easier. You'll get the same answer either way, so it doesn't really matter. So you could look at it and say, well, the second one has smaller numbers to deal with or fewer numbers to deal with, so we might want to do the second one. I personally would look at it and say, well, if I plug into the top one, I don't have to do any other special mathematical properties. I'm just simplifying with PEMDAS. So I'm going to take that and plug into the first equation. So I have y equals 2, and I'm plugging in that 4 for x. So negative 4 plus 2. So again, I took the answer from down here, and I took the equation from up there, and now I combine that to have this new equation where I'm only solving for y. And to solve for y in this one, all I got to do is simplify. So 2 times negative 4 is negative 8. Negative 8 plus 2 is negative 6. And I already have the second half of my answer. So we have our x value of negative 4. We have our y value of negative 6. And that would be our answer for this problem. Now, substitution is going to be the easiest to use when one of the equations is already set equal to a variable, like this top one was. You won't always have the equations already set equal to a variable. So, could you still use substitution? Yes. It would just take an additional step, because you could have to solve one of the equations for a variable first. Get one of the variables all by itself. So, I'm going to give you some steps again, just like I did on the last one. Now, the steps here are going to be a little bit longer, so if you want to just listen as I write them down or copy them as I go, you can do it either way. Again, I will end up posting the notes online. So, the first step here is to set one of the equations equal to a variable. We didn't have to do that on this one because we already were given one. Now, we're going to take a look at another problem here in just a minute where we do have to do this first step. So set one of the equations equal to a variable. Then we're going to substitute the variable in the second equation with the values from the first equation. So substitute the variable in the second equation with the values from the first equation. And then it's a matter of solving. So then after we did that, we had plugged it in, then we went through the process of solving. So solve for the variable that's left. Once you've solved for that first variable, we're going to take that variable and we got to substitute it back in to one of the original equations. Substitute the answer into one of the original equations. And finally, once you have it plugged in, then we solve. Yes. Is that good, or you need it higher up? And finally, what we did last was we solved for the other variable. So again, like I said, it's not the shortest process, but it's the same each time no matter what. So again, it's not a hard process to follow. It just takes a long time. I personally think that the last one that we're going to do is the easiest and the fastest method, but it also requires a little bit of substitution at some point too, because the last one that we're going to do is solving by elimination. And you started off by doing solving by elimination, but eventually, just like you get one answer here, you're going to end up plugging back in and using substitution again. Now, with this process, again, it's a little bit longer, so I'm going to have you guys try one on your own here, but I'm going to start you off on it because on this one, I didn't give you an example of having to do that very first step. So I'm going to give you a problem where you have to do that first step, and I'll show you the first step, and then let you complete it from there. So on this next problem, we're going to have, for number 3, again, we're still doing solving by substitution. We got 4x minus 4y equals 4. And the second equation will be x plus 3y equals 5. Can I cover up the rest of this? All right. So on here, now we didn't have to do the first step the last time because we already had one of the equations set equal to a variable. This time we don't. So for this one, looking at those two equations, which equation do you think it would be easier to get set equal to a variable by itself? Why do you say the second one?
Because it already has a variable by itself.
Because this variable, it doesn't have a coefficient in front of it, so it's almost by itself. The only thing we'd have to do is move this 3y over to the other side. So if we take this second one and move the 3y over by subtracting the 3y, and that's the only step we'd have to do to get x by itself. So we'd have x is equal to 5 minus 3y. So now that we have this x by itself, we can use this value that's equivalent to x and replace x in the first equation, just like we did on the last one. So again, substitute that value in. And I'll leave you at this point. This is where I'd like you guys to take over and finish the problem. So you guys are going to be solving for y first, and then solving for x. Again, if you're stuck, it's pretty much just like the other one, so go back and look at it. You're probably going to have to distribute first, combine some like terms, and then start isolating your variable. Yeah, the pass, I don't see it from here. It might be on my desk. wait this period has to go to the bathroom, right? I don't think those are all right. Go ahead and do it. All right. Can you give her the pass right there? This one? So, okay, we did this one. So we multiply here. That should make negative 12. That's why then the negative 12 and negative 4 would be negative 16. This was positive, that was negative. So we go back through. The rest of your work was fine.
When we get our final y answer, do we plug it into the original?
Mm-hmm. You can plug it in. That's actually an option of 3 different equations you can plug it into.
So we can plug it into the equation we just changed.
Mm-hmm. That would also work. Let me go ahead and show the work here and see. So, on here, again, as we went through, this is where we left off, right? So from there, you're simplifying. So we could distribute the 4. So the 4 actually got distributed to both of those terms. Then, after it was distributed, we could go ahead and combine like terms. So we had 2 y's. Those combined together to give us negative 16y. Then we could go ahead and isolate our variable. So we had to get the 20 over to the side. We subtracted it off. Then we had the negative 16 to get rid of. So we divide off negative 16 from that side. And we got positive 1 because 2 negatives gives us a positive. Once you got your answer for y, you have an option of 3 different places you could plug it into. Now, it doesn't really matter which one you plug it into because you'll get the same answer no matter what. But you could plug it into either one of the 2 originals at the very top. But again, if you plug it into either of those, you're going to have to solve. Or we took one of those 2 original equations and rearranged it so it was already set equal to x. And x is the other variable we have to solve for. So we could just take that one and plug it into that one. Because that's still our original equation. It's just rewritten in terms of solved for x already. So if we plug into that one, there's no more solving. It's just simplifying, and that'll give us our second answer. So again, there's more than one way that you can do it from that point. But again, they should all give you the exact same answer no matter what. So if you plugged into one of those top 2, you should have still got a 2 for your x value. Any questions? All right. So then I want to go ahead and talk about the last method, which is our combination method. Now, different books call this last method different things. Some call it combination, some call it elimination. So I'm going to title this one, Solve by Elimination or combination. Now, just sat at my desk. So depending on what other math classes you had and what other books they used, some of them might have called it elimination, some might have called it combination. There's no difference between the two. It's the exact same process. The names are really doing the exact same thing. It's just when we do this process, we're going to take our two equations that are given to us, we're going to add them together or combine them. But as we combine them, we're going to also eliminate one of the two variables at the same time. So some people call it combination, some people call it elimination, but it's the same thing. So for this fourth one, we have negative 4x minus 6y equals negative 6, and negative 12x plus 6y equals negative 42. Now, on this one's already set up for us a little bit, because normally we have a little bit of work to do first. In order to use elimination or combination method, you normally want to get your equations into standard form, so that ax plus by equals c. And you also want to have a pair of opposite variables. So on here, both of these are already in standard form, and we already have a pair of opposite variables. So we have a 6y where one is positive and one's negative. And the reason why we want that is so that we get something to cancel out. So we're going to first combine these two equations by adding them together. So we're going to add the first two together, gives us negative 16x. We're going to add the second two together, and it gives us 0y. Which, do we need 0y? No. So when we combine them, they get eliminated. And then the last two, add those together and we get negative 48. So now that we have got one equation with only one variable, let's go ahead and rewrite it so that's easier to read. We can solve. So we're going to solve this by dividing off the negative 16. And we would get that x is equal to 3. Now that we have x is equal to 3, we can take that and we can plug it into our other equation. So we have negative 4 times 3 minus 6y equals negative 6. Now, I chose to use the first equation. Doesn't matter which one you use. No, you could have used either one. All right? So we have a little bit more solving to do. So we're going to solve again. First, multiply this out. So you'd have negative 12. You still have a negative 6y. You still have a negative 6. We got to get y by itself. So we're going to get that 12 over to the other side by adding. So now we have a positive 6 after we add that 12. And finally, get rid of this negative 6 by dividing it off. And y is negative 1. Oops. So our answer here is x is 3, y is negative 1. So we have the coordinate point 3, negative 1. Now, we're almost out of time, so we're going to have to finish writing the steps for this one tomorrow. So we'll pick up on this tomorrow. We'll write the steps out, and then once we do that, again, we'll do a few more practice problems, and I'll have a worksheet for you guys. So, but that's it for today.